Okay. So yeah, real quick for everyone in person, can you mute yourself? Just because otherwise we're gonna have a lot of feedback and it's gonna be gross. Yeah, I don't know what's going on with this. So the reason, yeah, in person people are in Zoom is because EduRoom isn't working and the lab instructional, like the lab machine kind of rooms, the projector needs EduRoom to actually be able to connect because they upgraded it and then got rid of all the hardware like equipment. So we don't have a backup, which is kind of annoying. So yeah, we're going to just get started. So today's discussion section is kind of covering last week's content and then a little bit of the tail end of the previous discussion that we thought was like C is already too long. So we just kind of stuck it on this discussion section. But yeah, so today we're going to be talking mostly about floating point and we're going to be doing some memory management questions as well. So for anyone who just joined, here's the check-in link for today. If you could fill it out as soon as you can, that would be great, just so I can get a better sense of how everyone's doing, who's dying a little less, and just what general topics everyone feels comfortable with and just least confident about. So just from the initial responses, it seems like we're feeling pretty okay about like general number up stuff and then single precision. And then we're just not feeling great about memory stuff overall, which is 100% reasonable. So before we get to the pre-check question, how do we feel about just going over memory management itself entirely? Yes, this will go over discussion 3 worksheet as well. Yes, yes for memory management. Also, this is to in-person people as well. Yes, some review on that. Okay. Yeah, so just I realize also I can't screen share. Yeah, so for anyone who's joining in person, just be sure to mute yourself and turn off your audio because otherwise there's going to be weird reverb stuff going on. Yeah, okay, let me pull up my slides. Where's my slides? There we go. Okay. We're going to briefly cover, just go through kind of some general C stuff from last time. So I'm just going to go through the slides that we have here. So remember last time we covered the general memory structure. So as a really quick review, hi, welcome to discussion. Can someone fill him in just because of all the weird stuff? Yeah, we're going to go over some memory structure stuff. So as a just brief reminder, the code and text stuff of memory is at the very bottom, and it includes things that's included in the executable itself. So this includes stuff. It includes things like the actual code, like the executable that you're running, as well as some constants. For example, like if you're doing 1 + 1 or x is equal to 1 + y with y being some other variable somewhere else, the 1 in there would be in the code section because there's really no other way to represent it. So it's considered a constant in that sense. And then we have our static data. Sorry, the slides are a little jank because, oh, actually, can I present it? I'm not going to try this anymore. I'm not going to try any of that. We're just going to go with this. Oh gosh. Okay, let me. How do I get out of this? I don't think I can present very easily on here without having to go through everything, unfortunately. Yeah, no, it's not going to let me start from. Oh wait, maybe. I think it's going to let me start from here. Okay, cool. Yeah, and then we have our static and data section, which is right above that, and that includes things such as global variables, which are things that are declared outside of the code itself, and things that are preceded by a constant, the const modifier, and that tells us basically that the value is a constant, and you can't try to replace that. And these are, yeah. These are things that usually don't need to be changed. So it's usually in rapid access memory. And so this just means it's typically sitting in main memory and not in disk. We're going to skip over this for now, just for the sake of time, not super important. But yeah, one thing to note is that global variables can be changed. So for example, if you have an array or just something that you're using to keep track of like global state or something, that's 100% be sitting in static and data memory. Any questions so far? So this is primarily review from last section, but it's just to refresh things a little for the first section. Yeah? Oh, sorry, I thought there was a question. Okay. So then we have our heap memory. We spent a lot of time last time talking about this, but heap memory are things that are dynamically allocated. And just as a reminder, dynamic allocation just means that you're making a request to the system and telling it to give you a certain chunk of memory that's continuous. And it tries to do that. If it doesn't actually, if it isn't able to do that, then it's going to return a null pointer, which is just 1 byte of zeros. And you always want to check for null when you return from something like that. So this kind of memory is usually read-write because we don't want stuff that we can write to be executable as well. And it must be manually free with the free command. And so free just says, I'm going to take all of the memory that you just, or the pointer to all the memory that you just gave me, and then put it back on the free list so that we can use it elsewhere. So something just to note, you're going to be starting project 2 relatively soon, probably in about a week or so. And so in one of those sections, you're going to have the option to save stuff on the stack because you'll be able to manually manipulate the stack. And you'll also be able to malloc things. And so the default just becomes like, hey, let's just malloc stuff so we don't have to worry about stack things. And so that like shows you the concept of fragmentation and why that might be kind of bad. Just because when you start doing that and mallocing a bunch of little things, it's going to be really hard to keep track of all those pointers. And so you're going to have to malloc small things in the free, malloc free. And if you do that enough times, it's might actually cycle. I'm not sure if, I think there was one student in the past who actually managed to crash their code because of that. So I would just avoid that in general. So mallocing or dynamic allocation is for usually large things or things that you want to be able to access when you return from a function. And then we have our stack, which is automatically allocated by the system. It's read-write memory. It'll be freed by the system. I also realize I keep looking up here, but nothing's there. And then it goes top down. So this is really, really important again, because when you start manually manipulating this stuff, we'll see this in the next discussion when we start looking at RISC-V code and start really talking about it. But this means that whenever you're allocating more space for the stack, you're going to actually subtract from the stack pointer because you're going lower in the stack itself. And then when you're freeing up space or making certain things invalid, then you're going to add to the stack because you're now bringing the stack pointer back up. So if we take a look at this, stack pointer starts at the very top. So we know that those are the highest memory addresses. So to make more space for the stack, you have to subtract from it. We went through a bunch of function calls last time. Does anyone want to go through any of the function calls this time to look at? There was one that we didn't go through last time, but I skipped it for the sake of time. Not that one. Let me pull it up here. Let's see. Yeah, there are like 10,000. Okay, so we went through the general like, oh, this is what happens like when you just do a very, very normal function call that's like completely dummy. And then we saw that like the stack eventually got kind of quote unquote cleared or inaccessible. So we weren't able to actually access anything. So our solution to that was, hey, let's malloc a pointer so we can access that afterwards. And so we saw that that was an issue because we're like, okay, if we don't return the pointer, then it's going to result in memory leaks. And so the alternate one that we kind of solution to that was like, okay, then we'll return the pointer right here. We can see with int temp pointer, and then we're eventually able to free the pointer. And so that gave us one solution. But we also saw that like this is just mallocing space for a single integer, which is 4 bytes in our 32-bit system, which we've already kind of said that like is not super, super great. So this was the one that we skipped was the alternate pointer passing usage. And this is something that sometimes gets used in C and sometimes gets used in RISC as well. But any thoughts? Do you want to cover it today? Yes? Heard one yes. Yes. Okay, cool. So this one shouldn't take up too much time. Okay, let's present this again. Okay, cool. So just kind of recalling to last discussion and a couple of minutes ago. So we remember that whenever you return from something, the stack pointer kind of goes up. And then so everything that kind of it just leapt past, all of that's inaccessible. So it means that if we're trying to return a pointer, say to a struct or an array or just some item, then we're unable to do that anymore because it's going to be a local stack pointer. So our original solution to that was say, hey, let's malloc that, but say if it's for a really small struct, maybe like 8 bytes or something, that's not super efficient because then we just have a very small sliver that's been taken out of the free list. So sometimes what ends up happening is if we look at, I'm going to ignore that over there. If we take a look at what is going on here, our function call looks pretty much the same as last time, except we notice that the temp malloc kind of thing is crossed out. And instead, we're going to pass in an int pointer. So if we, can I go back? Yes. So if we go back and look at the previous dynamic allocation, we see that there are only 2 arguments. And then when we go to this one, we see that there are 3, with one of them being an int pointer. So we've just set up everything like we did before, with the main difference being we have another random variable that we just declared called temp, and we notice that we don't initialize it to anything. And this is just to set up some space for us to save values to in the future. So we notice that temp is sitting on the stack and it's above the current stack pointer. And it's also above where we're going to open our next function frame. So when we did that and we kind of called dummy, we can see that temp is still like above the dark section in the stack itself. So we know that once we say if we return from this function, it's going to look something like that again, which means temp is still accessible. So far, we're good. So once we actually have that going on, then we're going to go to our next part. Actually, before we do that, we're going to look at our setup. So our setup looks a little bit different, with the main differences being, okay, we have arg1 from the bottom, and then arg2, and then we have the address of temp. So the ampersand, as to recall, is referring to basically getting the address of whatever variable comes after it. So this means that we're going to look at where temp is, and I wonder if I can write on. Does annotate work? I want to say probably, oh, I can't. I want to say annotation. Oh yeah, on here probably doesn't work. Oh, that's sad. Okay, I'll annotate, I think, on the main screen and just hope that it works. I don't think I can annotate. Never mind. Okay, so I'm just gonna try to generally. Oh, you can't see my mouse either, huh? Because I'm not screen sharing from there. Okay, so if we just take a look at our temp right here, from the top, let's say our addresses are really high. Let's say it's address E. And so our old stack pointer was at, let's say, address E, which means that temp is sitting at address E. So whenever, when we try to get ampersand of temp, that particular block is going to have the E address in it. So once we do that, then we're going to go into the dummy function and say, okay, now we're going to take, we're going to dereference whatever was there in our temp variable. So if we look at the function header right there, that's the pointer, which is the address of the original int temp. And then so we're going to take that, go to that address, set it to be arg2, and then return. So what that means is now we're going to look at, if we can see vaguely, the kind of ampersand temp is kind of highlighted. And so we know that that variable kind of section or segment in the stack has this memory address. And now because of the dereferencing operation, we're going to follow that memory address to where it is, which is where the old stack pointer was, because it's just because of our setup, that's not always going to be the case. So we follow it to there, and then we're going to set it to arg2, and we're going to set 4 bytes worth of memory, because we know that this pointer was an int pointer. So now it's going to be set to whatever temp was, or whatever arg2 was, which in this case is going to be 2. And so now we're all good so far. So then we're going to return arg1 plus ampersand of temp. And so then it's going to return just 1 plus 2, and then we kind of go back. And we notice that temp is still preserved. And so that means that if we try to say printf temp in our main function afterwards, we're still able to do it. We're still able to print 2. And that's just because temp is sitting above where our stack pointer is now. So it's not in the grayed out kind of area below, but it's in the dark area on top, which means that it's still accessible and it's still active. Are there any questions? Feeling okay on that? Okay, so the main thing I would say to take away from this would be that where a variable kind of lives, its initialization, so what's returned when you do ampersand variable is different from the value that it holds. And the main thing that would might trip people up here is the fact that like when you're saying, okay, so what does this like dynamic, what does say like, if we go back a couple of slides, if we go here and say, okay, well, if we do ampersand temp, where do we think that'll sit in memory? So ampersand temp, yeah. So it's let me see. There we go. The thing that's bolded right now. So if we did say printf ampersand temp with the proper formatting, what kind of memory address would it return? So which of the sections in memory? Would it be okay? So we have one vote for the heap. Any other thoughts? It's tricky, don't worry. Yeah?
I was gonna say the stack because it's like a pointer. Like
So,
the temp memory exists on the heap, but it's pointers in the stack. So when you do ampersand temp, it's like memory address.
yeah. So I wouldn't really call it a pointer. I would just say the difference is between like when a variable is declared versus initialized. So temp is declared on the stack and then it's initialized to some value in the heap. So the value itself, if you're say like, oh, I'm going to dereference, or I say I'm going to print f, just temp, the stuff that gets printed out is a memory address on the heap. So that stuff lives on the is going to be in the heap. But if you try to do the ampersand, then that's going to be in the stack because that variable itself is living in the stack. Does that difference make sense? Kind of. Yeah. Yeah. So when you have trying to figure out where of these many places to write. I'll just direct it towards. Okay. Actually, let me see if I can. Okay, I'm gonna spotlight this because I realized last recording I was just a teeny tiny dot in the middle of everything. So hopefully this helps a little bit. Okay. So what we have basically is, so we have a function here. And then, okay. And then we have our, say, star. And then we're just going to do our malloc thing. So this is just, but we're not actually going to write it out really. So what happens here is, this is something that you'll see on an exam. I think it was probably on last summer's final, I believe. But basically there's three kind of things that sit here. So we have ampersand pointer, and then we have pointer, and then we have star pointer. So these three things all kind of produce different results, right? So what does star pointer do? So if we try to print f and then do format star pointer, what kind of stuff will we get out? So knowing that it's an int star.
What are the malloc returns, right? So would that be the memory address?
This wouldn't be the memory address. It goes to the memory address. But say if we do like say print f, and then what kind of stuff would it? What data type would it spit out? Huh? Integer, right? Because it's an int pointer. So this gives us an integer, and this integer lives on the heap. Okay, and then, huh?
You can't see the green on Zoom.
Oh, okay. Good note. Thanks. You can't see red either. Lovely. That shows up great. Okay, two of the markers work on Zoom. Do we have an eraser? We have an eraser over here. Okay. Thanks. Okay. Our chicken scratch we will erase. Okay, so if we try, I'm just gonna move this bracket because it's not super important. But if we like did printf here, We're gonna spit something out that's an integer on heap. Does that make sense for everyone? Okay, so then if we go kind of one above here and we say, okay, let's do printf here. What would we get here? Memory address, right, exactly. So we get a heap memory address. I'm going to abbreviate memory address with MA. But the kind of the difference is this memory address sits on the stack. So remember, this integer is in the heap because we followed some memory address to the heap. But this memory address is a heap memory address. So in value, it's somewhere in the heap, but it sits on the stack because the pointer was, this pointer was initialized, or sorry, it was, declared on the stack, if that makes sense. So the value here, it sits on stack. So it's a heap memory address living in stack. Does that make sense? Slowly, we're going to get into this gets progressively weirder. Okay. I think our two AIs are monitoring the chat, so I'm sorry if I don't see it because we're going back and forth. So far, we're all good? Okay. So then our last one, ampersand pointer. If we did printf here, what kind of result would we get? Yeah?
Is it going to be the memory address on the heap?
Not on the heap, but it is a memory address. So we have a memory address, but this memory address is, okay, first question is, where is this memory address? Like, what kind of value does it point to? So this memory address was some value that would be like mapped to heap. Where would this memory address map to?
The memory address of the pointer in the stack.
Exactly. So memory address of stack. But where does this live in memory? Huh? Also on stack. So the difference between, okay. So I guess first and foremost is the difference between these two is that this particular value was created during, I guess, this function call, but this particular thing was produced, or I guess, during the actual compilation of the code. So this is actually going to live in code. And the reason for that is because, okay, so we kind of go from bottom up. So bottom one reasonably makes sense. This one makes no sense. So the going from bottom up, we have an integer. And when we think about it, we're like, okay, well, there's some kind of memory pointer and it's pointing to this section. And this section we know is on the heap. And it's going to be some value. So let's say it's just a byte. So some value there, it's 4 bytes worth of stuff. And so this is an integer on the heap. But then what's kind of led us here, right? This is our first memory address. This is memory address 1. The thing that's nearly unreadable. So memory address number 1. So that memory address was stored in kind of somewhere else in memory. And this is somewhere in stack. Let me bring this over for online people. And we know that this was called pointer. So this particular 4-byte block is called pointer, and that's going to contain memory address 1. But what actually contained this? That's the question. So how did we get here? I'm going to go down actually for the sake of space. So what led us here? Well, something did lead us here. this particular stuff was somewhere in memory, and then it got executed, right? So when we were going through like all of these different slides, like it was kind of like, oh, we highlighted each of these parts, like things are happening, and that's kind of the execution flow. So each line is progressively is getting executed. We have to remember that these different lines, each of these lines is living somewhere in the active memory kind of stack. And it's living in the code and text segment. It's just that we don't really think about it because it's taken care of by the system, but it still exists there. So at a certain point, like we have to reference back to the code/text section of memory in order to know what else to execute. So that's why like when we kind of eventually refer to kind of the address of the pointer, like that address of the pointer itself is on the stack, but we have to refer to it somehow. So that kind of original reference is in code and text memory. So what this is actually kind of called, like this location, so this memory address number 2 that we're kind of referencing, that's kind of confusing. This is actually going to be the instruction itself. So how many people here kind of like have seen / heard / caught whiff of RISC-V at some point? Kind of, sort of, okay. So kind of something that gets covered there, but we're going to talk more about this next week, is just the idea that all of these instructions that are really complex can be broken down into basically step-by-step instructions. And that's what we're sort of looking at here. So at some point in assembly, pointer is going to have been like defined by assembly and say, okay, this line, we're just going to kind of create pointer, and then we're going to set it to some value, which then kind of goes through this entire process. So kind of at the end of the day, all the variables that you see and like their initial references live in the code and stack. Does that make sense? Huh? Yes.
So anything with an ampersand is like going, even if it's outside of a function, will be in the code. Is that correct?
So the question might be worded in a way. Okay, so if it asks, like the question asks you like, oh, where does this variable live in memory? So the variable itself lives in wherever like of these 4 different segments that we see. So like pointer lives itself is in the stack, but the memory address, this is kind of going up, but the memory address of it is in code.
Because right now this example is in a function, right?
Mm-hmm.
So if it was outside of a function, like the pointer would point to something on the heap, or
in static, right? If it were outside of a function, in static.
Okay, yeah, in static, and then the ampersand of the pointer is still going to be in code.
Yeah, so the ampersand of it eventually will lead back to the code section because that's where everything originates from. And so once things start getting executed, that's when like all of these positions in heap and stack and stuff start like existing, if that makes sense. So like say if you have something loaded into memory, nothing on the stack and nothing on the heap will exist. Some static stuff might exist, and then you'll have your entire code section, but the stack and heap will be effectively empty because nothing was executed. Only through execution does the stack start bumping down and the heap kind of starts going up, and then you'll have all of these other locations. Does that make sense?
I'll rewatch it.
Yeah, just take some time to digest. And maybe some examples will help. So all of this was kind of in preparation for question 2 on the what's it called? The discussion sheet. So it's less complicated on the discussion sheet, but this was something that showed up on a past exam. So that's why it's important. It tripped up some TAs when we were pre-testing it. So it's important, but I'm gonna give you guys probably, let's see, how many questions are there for this section? About 5 minutes to work through 2.1 actually maybe 3 to 4 minutes to work through 2.1 and 2.2, and then we're going to go through a couple of examples later, and then we're going to jump into floating point. Sound good? And also online? Okay, cool. And also anyone online or in person, feel free to drop messages through Zoom if you feel uncomfortable like breaking the silence or anything like that. So And also, yeah, feel free to work in groups and discuss together. So like the little pause you see right here. And also, if you don't understand this, feel free to talk about it in your groups and we'll walk around and try to answer any questions that you have. Okay, it might not have been enough time to, I think, answer everyone's questions exactly. I know there were, I think, two main big questions that we'll address up here. But yeah, for the other parts, so not A and then not G. So not the first or last ones. Are there any questions about why the answer is the way it is? Or actually, did everyone get to check their answers? I forgot to ask that. No. Okay, so let's do that first. So for the first, for part B, local variables, where are they stored? Stack? Yep, sounds about right. Global variables? In where?
Static.
Yes, static. Because remember, static is not just read only, it can be write, but it's going to be accessible to everyone. So it needs to be somewhere like that on in memory. Constants, where are they stored? So feel free to throw out your answers. Lots of places. Great. So what places? Lots of places.
If it's hashtag defined in code,
Uh-huh.
outside a function, it's in static. If it's inside function, it's in stack.
Yeah, so that's right. So to repeat, so if it's in local kind of or within a function, it's going to be on stack because that's still considered a local variable, and you don't want constants that are declared locally to be like present for every single like everything else that you run. And if it's in global and also a constant, then it's going to be in static memory and in read only in this case. And if it's something like, for example, sorry, remind me of your name. Zach. Okay, if like what Zach says, so he said pound sign or hashtag define. So if that feels a little bit confusing, it's because we haven't really explicitly talked about it. It's considered a C preprocessor directive. Nick mentioned it in the lecture for about like 2 minutes, but we're going to talk more about that in the call discussion section and in the call lecture. So if you're feeling confused by that, it's totally okay. It was 2 minutes worth of stuff. But basically what that does is anywhere that you see kind of a hashtag without a space and then like say define or include, what it's saying is take what comes after and then basically just copy paste it into this part of the code itself. And then that happens before things get compiled. And then what you end up with is probably a bigger file. And it's just a shorthand way to reference say libraries and maybe like other things. And so then once it gets copy pasted, then it gets compiled. And so it resembles kind of what you would see like, so like example, x is equal to y plus 1. So it's like the plus 1 part of that. So it sits in code itself. Does that kind of make sense? Okay. Then moving on, we have our machine instructions. So where do those live? Code, right. So if anyone hasn't watched the RISC-V lectures, so machine instructions are basically just assembly, and assembly eventually just gets manually converted into binary, into bits. And that's the stuff that's going to be stored in the executable after doing some more magic on it. And so that's going to get loaded into the code and text section. So that's when machine instructions fall in code. What about the result of malloc? Where does that live? Heap? Yes. So anything that has some kind of character, word, and then alloc at the end. So that's considered dynamic allocation. That stuff will always live in heap no matter what. Okay, so now for the first and last one. So the easier one to kind of answer is static memory or static variables. Per the name, static variables will live in static memory. What static variables are actually a little bit funky. They're things that you see like literally static and then int and then the variable name and something else. In C, it basically just means this is private and shouldn't be exposed to like the user. And so it'll kind of live in static memory because it's not really expected to be changed by the user and thus will not change during the execution of the code unexpectedly. So that's why it lives in static. You see this in project 1 a little bit, like you'll see static functions, stuff like that. it's kind of like if you don't use it, it also works. Like, so if you delete all the statics from your project one, don't do that. But if you delete all the statics from your project one, it'll still run fine. Like it doesn't, it just means things aren't exposed to the user basically. So it's kind of like private in Java, if you remember that from 61B. Make sense? Okay, so then for the last one, we have our string literals. So string literals are basically just strings. And so we have here 4 different versions of ways that you can declare strings, just because C's like that. And so for the purposes of clarity, I've kind of like gave the answers away a little bit in terms of how they look. But for the first one, what we have here is a string. This is the string literal part. So like this part, these are the actual string literals. And then the part of, like on the left-hand side are like things that refer. So it's the variable initializations. So for this first string literal hi, we have a car pointer to that. And so this results in a string that lives in static memory. So this hi on the right-hand side, it can never get changed again. It'll always stay like that. So the hi itself is going to live in code. This variable is going to live in static. So when we refer to say, oh, where is static string in memory, then it's going to be in static memory. But these like themselves are kind of like the x is equal to y plus 1 kind of example. It's like the 1. So it's going to live in code memory. But this lives in static per the name. Does that make sense? So the pointer itself here, like we don't really see pointers outside of say mallocing things. And that's why this is kind of special. It's because it's saying, hey, I have a memory address and by default, it's going to be 3 characters long, no more, no less. And I won't allow you to change it because this thing got loaded from code and it's a reference to this. And because it did that, I'm just going to say and like make it known that everything is going to be static and things can't get changed anymore. So unlike like some of these other ones later where it's like, oh, I don't necessarily know what's going to go in the string itself. I just know kind of what size it is. So that's why these 2 in particular are kind of by default mutable or changeable. So I'll kind of talk about those 2 in a second. Does that make sense for the first one? Okay, so then for the second one, we have a string literal again, howdy. And so this one is slightly different. So we notice that the variable initialization here is a car array. And so the difference between these 2 is now this one is like, see, I have a trick for you. I'm going to make it a car array and thus whatever you have here is actually going to be changeable. So this one is you cannot change it. This one, you can change it because what actually happens is it takes a look at code memory, which is still where this is sitting, and says, okay, I have 1, 2, 3, 4, 5, 6, and then the implicit null terminator 7 characters here, so 7 characters. And I'm going to make a car array of 7 characters. And I'm just going to copy everything that you have here into the car array, but later on, you can still change it. Does that make sense? Okay, and then these 2 are a little bit more self-explanatory, I think. So this one is a heap string because what we ended up doing is even though we have a car star, because it's malloc, it's going to be on the heap, hence heap string. And so everything on the heap is by default mutable or changeable, so you can write to it. So what needs to happen here is you need to malloc the size of the character times whatever length of string that you want plus 1. And that kind of plus 1 is just for the null terminator that you'll automatically need by default. Make sense? Okay, and then for this last one is just the car array. So this one is typically just non-heap strings. So we know like because mallocing kind of winds up on the heap, but we don't always want things to go on the heap. So this is just a way to make things not go on the heap, but still be mutable and still not like say, oh, I know what my string is. Because sometimes like we don't know what data we want to put in there. We just want to allocate some or have some space for things eventually to go in there. And so that's what in this becomes useful. So it just gives us most likely a local, unless it's global, in which case then it's static, kind of non-heap string of size 7 or whatever you put in here. So n plus 1. Are there any questions? Yes.
So the first one is reading the I is in code, so it's pre-processing that. And then the actual like pointer is in static. So you can't change that pointer to point to something different.
Yeah, exactly. Yeah, so it's not exactly pre-processing it. It's just kind of saying this stuff is things like the +1 in here. If we don't look at what's declared over here, we don't really have any way to reference to it unless we just kind of shove it in code, which is kind of just things that go here that we don't have things that go in code is basically we don't have any other reference to it. So it's kind of by default where things go. So that's why this stuff goes in code. And then we, by happenstance, managed to create a reference to it. And so then that's when like these variables kind of get created and then filled. So that's why like these two kind of components live in different places.
So if you have like int x equals 5, is that 5 from code?
Yes. But the I part is either in stack or static. Are there any questions? Okay. We're gonna move on, shift gears entirely, and then go into floating point just because we're about halfway or a little over halfway through, and this is technically a floating point discussion. But yeah, so I realize also I haven't been writing anything on the Zoom screen, so let me know if that would be more helpful. Everything's kind of been on the board right now. But yeah, okay, bye. So we're gonna really quickly just go through the pre-check. I'm gonna give you guys a minute until 2:10 to kind of just go through, answer true or false, just to get a kind of cursory feel on how under a floating point kind of feels for y'all. Feel free to take a picture, screenshot. The slides are posted. They're also in the central resources post under. There's a heading called discussions. It links to unofficial course notes and all the discussion materials. So anything that I write on here or the slides, I believe. I'm not sure if I should link the video playlist there too. The video playlist will be there as well. So just anything kind of made during discussion. Okay, it's 2:10. Possibly not enough time to have gotten through all of them, but just in the interest of time, we're gonna jump into the pre-check. So first question, true or false? The goals of floating point are to have a large range of values and a low range of precision and real arithmetic results. Collectively, kind of true or false? What does everyone feel? Any thoughts? Online? Okay. Got a DM saying true because everything in there looks true. Okay. So in the interest of time, we're gonna just go through them. So floating point itself, one of the biggest goals of it is like we have our arithmetic numbers, and that does everything that we really need it to do, except for have precision. So we have like our scientific notation, we have everything like that we need to have decimals or really large values for. So the precision is the part that's kind of wrong. So here, a low range of precision is not correct. So that's why this answer is false. But floating point has high precision. That's also why we have the difference between single and double, single and double precision floating point numbers. So right now what we're doing with 32 bits is single precision floating point, and we see like we have a really good range of things. but it's ultimately not up to par for like what's needed in real life computations. So the floating point numbers that we usually use in most of our systems are 64-bit, but that's just terrifying to calculate. So no one's going to make you do that. For the second question, the distance between floating point numbers increases as the absolute values of the numbers increase. What do we think about that? I heard something true-ish. Got true online. Yep. So yeah, the answer here is true. And the reason for this is because we just have uneven spacing between the numbers. So in lecture, kind of we showed what a step size was. If you didn't watch lecture, I would definitely go back and kind of take a look at it. But step size is basically between, say, like if you increment by 1 for the binary string, what does that actually represent in terms of a step size in real kind of calculations? So that's saying like, oh, if we have 1, 0, 0, 1, and then we did +1 here, so that would give us 1, 0, 1, 0. And we know because everything is bits. By the way, I'm annotating on my iPad right now, so it'll show up on the screen. Because this can be represented or interpreted in a lot of different ways, we're thinking about floating point. So in floating point, this can represent some kind of step size. And that just kind of means, okay, +1 in binary equals plus how much in floating point terms. So the reason that things kind of increase is just because as we kind of cycle up, we'll eventually hit like a wall in terms of the value of the increase. And then so what ends up being increased is our exponent. So we'll talk about this in probably, I'd say, a minute and a half about the different components of floating point. And then for the last one, so later, and this is true. So for the last one, we have true or false. Floating point addition is associative. So associative just means that if you have A plus B plus C, if you do these two first, it's the same thing as doing, like, say, B plus C first. So true or false. So we have someone, yes. So yeah, it's false. And the reason is just because we have rounding errors. So as a reminder, floating point doesn't like round kind of correctly. It just kind of like truncates the bits that like kind of overflow. And so then what winds up happening is say if you had a really, really large number and then a really, really small number, you're going to kind of smush the bits together and do what's needed there. And then it's highly likely the small numbers kind of bits are just going to be chopped off. And then so you'll be left with a really imprecise number because you just lopped off a whole number, probably amount of like the decimal portion, or I guess binary portion. So this winds up being false. And it's because very big plus very small. And then plus say something big is not equal to a small value. And then plus say too big. And this is just because of the way that bits are kind of truncated and then rounded eventually. And it just means that like if we do two bigs together versus a very small and a very big, some number of bits are going to be chopped off at some point, and it's not going to be consistent. And so we'll lose either magnitude or we'll lose precision a lot. Are there any questions? Okay, we're going to jump into, so we're going to scroll up a couple pages back. So after the floating point section, if we do wind up having time, I'll come back and go through the latter parts of the question 2. So to someone who asked online. So this part is just going to be maybe like 5, hopefully 7, less than 7 minutes of just talking. But just as a general review, what floating point is talking about is a standard definition of interpreting 32 bits in order to make space and be able to like represent decimal values and then really, really large values. So this is the standard for 32 bits. When we have 64 bits, someone asked in lecture, it just kind of gets expanded, exponent increases in size, significant increases in size, and you'll just have more precision and more magnitude. So before we start throwing all these terms around, we have our 32 bits broken down like this. So we have first 1 bit of sign, and this is kind of similar to our signed representation where the first bit tells us whether something is going to be negative or positive. And so as per kind of like signed notation, if we have a 0, it's going to be negative. And then if we have a 1 here, it's going to be positive. And then for the next part, we have our exponent. So this part is what gives people a lot of grief just because of the way that kind of the exponent is calculated. So to make sure that we don't kind of like screw up our terms, I guess, I'm going to be referring to like what's here. So the unsigned representation of the 8 bits here, that's going to be the exponent base value, or base exponent rather. Unsigned 8-bit representation. And then you'll notice later that there's this thing called like that's exponent, oops, I crossed it out, but there's exponent plus bias and then exponent plus bias plus 1. And so I'm going to be referring to that as the exponent value. So hopefully that helps differentiate which one of the two we're talking about. And then the last part is the mantissa, or the significand. We're going to use the significand here because I guess it's just the one I kind of like, but they all mean the same thing. And so this portion is kind of what tells us what kind of value it's going to be. So it's kind of, you can kind of think about it as like the magnitude or the kind of base, the value of the whole floating point itself. The exponent kind of determines like the magnitude and how much the binary point gets shifted by. And then whereas the significand portion tells us, okay, so things are getting shifted, but this is like the series of 21 bits that are going to tell us our value. And so something else to kind of note is that we have a bias here as well. So the bias here is going to be similar to our standard bias that we saw back in number rep. So what that means is we're going to have our standard rep or standard bias is going to be equal to, for an n-bit number, is going to be equal to negative 2 to the n minus 1 minus 1. So in this case, we have an 8-bit number here because we're doing the bias off of the exponent. So that's going to give us negative, so n equals 8, negative 2 to the 7 minus 1. And that's going to give us a bias value of negative 127. So that's what we're going to be working with when we're talking about IEEE standard. On exams, you'll often be asked to do some weird like value with the bias is going to be negative 129 or like something kind of weird like that, or say exponent is going to be 9 bits instead of 8. So I would definitely pay attention to that. And then so how we actually calculate these values, because we have a really long binary string, but then we actually need to figure out what kind of value it's going to be at the end. And so we have 2 types of values. So we have one normalized and then we have one denormalized. And then we have our special values, which are infinity and then nans, which stands for not a number. And so these kind of all represent different things. So not a number. You might remember seeing nans if you do anything with Python that involves like pulling data from somewhere. There's a lot of nans when you do things incorrectly there, or when the data is poorly formatted. So the difference between normalized and denormalized floats, the main difference is the fact that in normalized floats, we have an implicit 1, and then in denormalized, we have an implicit 0. So what this actually means is when we take a look at a binary string, in the significand, so we have our significand here. Because we're always looking to increase our range and preserve what bits that we do have, if we notice that something's like, oh, this seems like pretty implied, so we're just the default solution is just going to be, oh, we're going to get rid of it. So but yeah, to have that kind of range, typically what we want is like, oh, we want 1 point something. So if you remember in like what's it called, scientific notation, the kind of default standard is to say like have 8.375 times 10 to the whatever, like 7. So we know that like once we roll over to say like 11 point ... whatever, we know that then we have to convert it to 1.1 and then ... whatever it is. So that's just kind of like the standard there. So a similar kind of thing exists here with normalized numbers. So because we want to preserve our bits and but we only have zeros and ones. So we know that the two numbers at the front can either be 0 or a 1. And so we've just kind of split it and said, okay, 1 is going to be denormalized, which is extra, extra small. And then 1 is going to be normalized, which is past that very, very small boundary, and then all the way up to really big. Does that make sense? Are there any questions? So in scientific notation, we have 0 through 9, point, ... But in here, we just have 0 and 1. Okay, so now that we have those two kind of split, the way that they get calculated is slightly different. So if we pay attention to how these look, the two differences here is we have a 1 point significand and a 0 point significand, like we talked about earlier. And then the other main difference is in the exponent and bias kind of plus or the exponent, base exponent plus the bias portion. So in normalized, we have just exponent plus bias. And then in the denormalized, we have exponent plus bias plus 1. The reason for that is because if we look at the chart here, we've kind of split up all of the possible notations for each of these sections. So what we're paying attention to here is the exponent. And so we notice that for normal values, we have our exponent be anything from 1 to 254. We leave out 255 just because we want to be able to represent other values. So we have all the way up to 254. And so we notice that that gives our exponent a huge deal of range. So that's all fine and dandy for our normal numbers, but then our denorm has an exponent of 0. And so that gives us 0 plus negative 127 normally. So let's say, so for denorm, we have 0 plus negative 127. But that is quite a deal different from, say, like what we have here. So for normalized, what our smallest exponent value is going to be 1 plus negative 27, or negative 127, sorry, negative 127. And that's going to equal negative 126. So once you start doing a few calculations, you'll notice that like if we have a difference in the exponent and then we're cycling through the significand, it's actually going to be a really big difference in terms of like the step size. So to kind of match it a little bit better and to make sure that we don't have a giant gaping hole that we just can't represent, instead we're going to just add this kind of like, okay, we're going to add a 1 so that like they're vaguely equal, and then so now we can go down from there. Because we already have the difference of the 1 and then the 0. So to create another difference there means that we leave too big of a hole. Does that make sense? Okay. So now that we kind of have a sense of how to calculate things, so conversion between the two is a very like systematic process. So the general kind of rule of thumb is if you have like a binary or hex value, or just say non-binary value, you usually want to convert it to hex first. So let's do an example here. So we're going to go with this FF94 and then beef. So for F and F, we know that they're going to be all ones. So we have 1, 2, 3, 4, 1, 2, 3, 4. And then 9 is going to be represented as 1, 0, 0, 1. 4 is represented as 0, 1, 0, 0. And then I need to move these closer together. And then B is represented as 1, 1, 0, no, yes, 1, 0, 1, 1. There we go. And then E is everything but the last bit. So it's 1, 1, 1, 0, and then 1, 1, 1, 0, and then 1, 1, 1, 1. So I'll just label this FF94. Just as kind of calling back to number rep, it becomes a lot easier to memorize the conversions the more you do. So if you're like, oh yeah, I still have to kind of go back and count through all of them, that's very, very, very normal. Okay. So now that we have this, what we want to do is now we want to split up these bits in terms of where the natural splits occur when we're doing the IEEE standard. So we're going to separate out our signed bit right here, and then we're going to separate out our 8 exponent bits, which is right here. And then the rest of it are significand bits. So before we go any further, does anyone notice anything unique about our sets of, I guess, our categories? And can anyone tell us what this value is right now? without doing any other calculations. Yes, yes. Oh, yes. Oh, the pink bars are, we're just splitting up the bits in terms of where IEEE splits them because we're trying to convert it. And so we need to know where like the sign bit is, where the exponent bits are, and then where the significand bits are. So we went, okay, 1 bit for the sign and then 8 bits for the exponent. And then the rest is our significand. Does that make sense? Okay. Yes. Wait, sorry, it's going to be equal to 1? Yeah, it's 255. Yeah. Wait, sorry, did you have a question? A number? Not a number? Okay. So yeah, so I think people are kind of realizing what's going on here. So this is not theoretically a great value for like conversion. And the reason is because we notice our exponent here. These are all ones and we have 8 ones, which means that it's going to be 2 to the 8 minus 1, which is equal to 255. So this is our base exponent value. And so if we look at our chart here, back over here, so this is the base exponent value. We know that it's either going to be an infinity or a nan, which is not a number because of the 255 there. So, and then we look at our mantissa or our significand, and we notice that it's very obviously not a 0 because there's ones in there. And so looking at that, then we can safely say, okay, this is going to be a nan, and then we don't have to do anything else. So we don't have to calculate anything else. Does that make sense? Why? Okay. So to make this a little bit more interesting and actually like able to be calculated, we're just gonna like take out a few of these ones and make them zeros. So now our actually let's make the top ones because calculation. Let's kill all of these ones and make them 0. So we have 3 ones down here. So our new number is going to be 1 0 1 0 0 0 0 0 1 1 1 and then whatever that stuff is. So now if we try to calculate it, okay, this is now not a number or a non-nan, and it's not infinity either because our exponent is not 255. So if we take a look at this, I think that's, remind me what your name was again? Kat.
Josh.
Yes, Josh. Okay. So you were saying earlier that we need to just subtract 127. And so because this is now a representable normalized number, we are able to do that. So 0, 0, 0, 0, 0, 1, 1, 1. This is going to be equal to 7. And then so if we try to calculate the actual exponent value, it's going to be plus negative 127, which gives us an exponent value of negative 120. And then because this is hard to calculate, we're going to make this all zeros, just to make it a little easier. And then so now if we have something like this, we can just now plug this into our formula that we saw because it's a normalized number, and we can say, okay, so now we have our floating point representation is going to be negative 1 to the 1 because we can match this to our 1 right here. And then we're going to multiply this by 2 to some value of the exponent. So we know that it's going to be 2, and then it's going to be 2 to the 7 plus negative 127 power. And then we're going to multiply all of this by whatever the mantissa is with the implicit 1. So we have our 1 point, and then we have 0, 0, 1, and then 0, 1, 0, 0, and then all zeros after that for a total of 23 digits. And then so this is definitely not something that you're going to have to calculate by hand or ever have to calculate. But this is just kind of a setup to show of how you would convert from a hex or a binary form into floating point. Does that make sense? Or are there any questions? Okay. So, okay, we have half an hour left, so that should give us enough time, actually, surprisingly. Just something I want to touch on really quickly before we hop into more examples and practice is that there's a lot of confusion about like, oh, how do we figure out like what each of these values actually are? And so a way to think about it is like, say, if you have the binary point right here. So we have our like Let's say we have a ghost 0 right here. And then we have our binary point. So each of these spaces afterwards, so this is at the -1 position, -2 position, and then -3, -4, etc., so on and so forth. What actually happens here is like on the left-hand side, we know this is like, oh, 2 to the 0, 2 to the 1, etc. So now this side is going to be exactly the same. It's going to be 2 to the -1, 2 to the -2, 2 to the -3, 2 to the -4. And so what that actually converts to is say 1/2, 1/4, 1/8, 1/16, ... all the way onwards. And so when you actually calculate it, you would convert that probably to a decimal format and then add them. Are there any questions? Okay. So we're going to give you guys a little bit of time to work on some of these conversions. I would focus on 8.25 for starters. And if you feel comfortable with that, then you can try the 39 one. And then I would say -infinity. So I'm going to give you about 5-ish minutes to work through this. If you want to move on or try any of the other examples, feel free. This is just kind of to get everyone started. And also for online, feel free to ask questions in the chat whenever. Okay, cool. So we're going to just come back to this beginning. I'm going to just walk through a couple of examples of converting each of these things, just in the interest of time so we can get to the last part, hopefully. If I can zoom in on this. Okay, so I'm just going to do 8.25 for now for the conversion from decimal to binary version or floating point representation. I'm going to do this with probably purple just to kind of make it different. Can everyone just see that's a different color from everything else that exists on this so far? Yeah? Okay. So we're going to do that right here. So we have our 8.25. So generally the way that you want to convert between when you have a decimal number already and then you want to convert it to a floating point is, okay, I'm just going to break it up into 2 parts and say I'm going to do 8 first. So 8 is represented in binary as 1, 0, 0, 0. And then 0.25 is represented as binary. There's a point there, but we're just, it's a very, very ghosty point. So we're, and then it's going to be 0, 1 right here. And right now, we don't want to really care about where this binary point kind of exists. So we're just going to kind of smack the 2 together. Like if we don't care about the decimal point, this could just as easily be 208 or 825, right? Like, and then we just said, oh, we're going to move this decimal place 2 times over here. So we're going to do the same thing with binary. So we're going to smack the 2 parts together. So 1, 0, 0, 0, and then we have our 0, 1. We're going to put that together. So now that we have that, that's starting to kind of resemble what we have in terms of a mantissa or a significand. So we're going to say, okay, well, we know that what it's supposed to look like is this 1 point and then something, something over here. So if we want to kind of try to emulate that, well, we're going to put our kind of binary point right here and then just take these 2 sections. So we know that already implicitly that there's going to be a 1 when we're converting, like when we converted from binary to the decimal version. And so that also means that we don't actually need to explicitly write this 1 because we're trying to get to the mantissa here, right? So once we have this, then we can say, okay, well, this is starting to sort of look like a mantissa because we don't need this leading 1 because we're going to, as a normalized number, we're always going to just assume that we have a 1. And so our mantissa, oh, I switched to using mantissa. Oh, well, is going to look something like this. 0, 0, 0, 0, 1. But this only has 5 bits. So now what we're going to do is just fill in a bunch of zeros all the way over here, such that the mantissa has 23 bits total. Are there any questions as to how we got here so far? So we're not done yet, but we've gotten the significand mantissa bit. Okay, so now we want to actually figure out the exponent part. So we know that by default, like the binary point is going to sit right after the implicit 1 here. And so when we actually kind of did the conversion, we knew that, well, we wanted the binary point actually to be right here. So we want the binary point to be somewhere in this vicinity. So we're going to bump it how many times? 1, 2, 3 times. So 3 times, that means our exponent value is going to be equal to 3. So how do we actually get the exponent value? Well, the exponent value is equal to the base exponent plus negative 127. So that means we have 3 is equal to the base exponent. I'm just going to write BE minus 127. So our base exponent is going to be 130. So this is now what we have to represent binary wise to get our base exponent for this section. So now we have to represent this using 8 bits. So can we do it? Well, we know our maximum for unsigned for 8 bits is 255. So this is significantly under 265. In fact, it's really close to 127, which is 7 bits of all ones. So what we can do is, well, we know that our very closest power of 2 is going to be 128. So closest power of 2 is 128. So that's going to be a 1 right here, and then 1, 2, 3, 4, 5, 6, 7, 0. So that's 128. So we want 130. So we're going to knock out a 0 right here, give ourselves a 1, and then that's 128 plus 2, which is 130. So our final answer for the exponent part is going to be equal to 1000, 0010. Any questions as to how we got there? Okay, now we want to combine everything that we have and then convert it to hex to make it slightly less ugly to read. And so we know we have a positive 128 right here. So our signed bit is going to be 0. If we had a negative 8.25, then our signed bit would be 1. So that's the main difference there. So now for our final answer, I'm going to put it in green. We're going to have our signed bit, which is 0. And then we're going to have our exponent or base exponent value. So it's 1000, 0010. I would highly recommend kind of separating it out in terms of groups of 4 based off of which section you're working on, because it's really easy to lose track of your ones and zeros here. And then our mantissa is going to be 4 zeros. So 1, 2, 3, 4, and then 1, and then all zeros after that. So now we actually want to group that into hex digits. So I'm going to use kind of the red color to group those. I realize also red is probably not great for that. So I'm going to use orange to group that. Hopefully no one's orange green colorblind. So we're going to separate these out into groups of 4. So we have one group right here, one group here, one here, one here, and then we have all zeros here. So that's just all zeros after that. So you notice that like they kind of look a little bit off from our original groups of 4, and that's just because we start with the signed bit and we want to make sure that we have our appropriate bits there. So now that we try to convert this, 100 is going to be 4, and then 0001 is 1. This is 0. This is another 4, and then we have all zeros over here. So our final answer is going to be hex 41040000. Are there any questions as to how we got there? Silence is either people are processing or floating point bores me out of my mind, either of which are totally plausible. Huh? Oh, yes. Sorry. Here, that should show everything. So the different colors, so purple is mantissa, red is this exponent, base exponent, and then the green orange part is putting it together. So these notes will be posted later as well in the same Google Drive. So the slides, any notes, they're all in the same drive in the central resources link. Yes.
The purple.
Mm-hmm.
Is that like 825 and then you have your like 2 new spaces?
Right here. Oh yeah, that was just an example to show like, oh, when we're looking at things, like we only really know like the value by looking at where the decimal point is. So like here we could just like put the 8 and 2 5 together to make 825 and then bounce the decimal point 2 to the left to make 8.25. So that was kind of leading into putting all the bits together right here.
Is that related to how in the next one you so 1.3001
And then move. Yeah, exactly. Because we were first identifying our leading one, got rid of that, and then our remaining mantissa, we wanted to figure out where the original binary point was supposed to be. So then we took that and then moved it however many that we needed to move. Okay, I'm gonna really quickly move on to, actually, just as a temperature check, would people rather talk about just like samples of C code and like working through that, or step size and like bounds on what can and can't be represented in floating point? So option 1, C, option 2, floating point. We got 1, 1, 2, 1, 2, 1. Okay. Okay. Anyone online have a preference? 1. Okay, I think we're leaning slightly more towards C kind of example, so we'll do that. Also, I'll stick around a little bit afterwards to talk about that, and also I will link, I think the notes talk about the bounds. If not, then I will write something up and then post them tonight to kind of explain that part. But I think there should also be past videos up for that as well. Okay, so we're gonna move back to part 2. So I would say, am I missing? Oh no, okay, I'm not missing a section. I'm gonna jump to 2.4 and 2.5, just because that's kind of the more complex section. So we're gonna just walk through the problem setup together, and I'll give you guys maybe a couple minutes to work on it, and then we'll talk about it together. So going through the question, switching back to C mine. Suppose we've defined a linked list struct as follows. So assume star list points to the first element of the list, or null if the list is empty. So this is basically a very, very standard setup, say if you want to make a linked list. So if you ever, for some reason, are doing a coding challenge or like an interview in C and you need to do a linked list, remember this because it's very standard. So we have a struct LL node, so linked list node. The first element kind of, or the int first, is basically telling us, oh, this is the value that's actually stored in there. And then LL node star is the rest of it. So basically how it looks is very similar to a linked list that you would see in Java. So we have our node right here. And then so the second one points to some other node in memory. So this is how the structure kind of looks. So very standard, nothing atypical from your standard linked list. And then so the last element is going to be a null. And so that's what's X'd out currently. So let's see. So implement prepend, which adds one new value to the front of the linked list. Hint, why use LL node double pointer list instead of LL node single pointer list? So give you guys a couple minutes to work on that. I think that's actually probably harder than the second one. So we're going to go over that. So keep in mind that the pointer to this is a double pointer. So it's star star LL node. I'm actually going to just erase this point arrow right there because I think that makes it a little bit confusing. So we'll just say that this is how it looks. Okay, just in the interest of time, because we technically have 1 minute left, I'll stay an extra, I think, like 45 minutes because we started a little bit late because the internet. But yeah, we're just gonna kind of walk through the solution here. And I would say like working with linked lists is something that's pretty, I wouldn't say maybe like common, but it's not surprising. For reference, like fall 20, there was this exam and they had to write code. And one of the questions, they had to write C code for the exam and it had to be compilable. And so one of the questions was on linked lists. So yeah, so working with linked lists, I guess just as a starter before we jump into anything else, working with pointers and then lists of pointers. So when we work with structs, we want references to them, so we use a pointer. If we want a list of pointers, we can't just use a single pointer because that would just reference a single struct. And so instead we have to use a double pointer to kind of refer to the entire list itself. So you can almost think about it as like a double array or a 2D array in that sense, where it's like one way is sort of like the struct itself, and then the other way is another set of pointer that references like all of them together. So if that doesn't make sense now, it might in a second when we start going through the solution. But okay, first things first, we notice that we have, I'll erase this to make it a little easier to read, but we have our struct LL node double star, which is the list itself, and then we have the value that we want to insert to the very beginning. So if we look at kind of our sample here up front, I'm going to just delete one of these just to make it a little easier to read. But so this is our LL node double pointer. It's this object. And so what we in theory want to do is add another node that does something like this. So that's what we're trying to do. And so eventually we want this to reference this at the beginning. So instead of referencing the second node, we want to reference the first node that we just added. So how do we do that? Well, first things first, I walked around and noticed that a lot of people were doing like malloc stuff. So that's absolutely right. First things first, we want to actually malloc a node. And this is a situation that you do want to malloc because structs are not inherently defined in C to be any size. So you need to actively say, I want to request something. So even if it's a very small struct, you still would probably want to malloc it in this case because you can't really do anything else. So actually, I take that back. If you didn't want to do, say, like heap one, you could like in theory like do it in brackets, and that would result in a local struct. But part of the reason that we don't want a local struct in this case is because we want to be able to reference this after we return from prepend, because this is in theory modifying some list that's not in this particular function. So that's why we would want to use malloc in this case. So we're just going to write this. So we have, I'm going to zoom in a little bit. So we have our struct LL node pointer that we're theoretically going to return, and we want an item, and we're going to typecast it to a struct LL node here, pointer, and then we're going to malloc size of struct LL node. So you'll notice that every time we use LL node, we need to include a struct in it. And that's because this is a struct. So we have not defined it to give it any other name. So if you find your code isn't compiling correctly or whatever in project 1 and you're using structs, this might be the case. It's really easy just to forget it. If you in theory didn't want to have that, what you could do would be to do a type def. So type def struct LL node, and then at the very end, what you could do would be like, oh, call it node or something. And later on, when you use it, what you can do is, oh, node star, and then say node is equal to whatever. So type def is kind of giving it a nickname. Difference between the two is mainly type def is used for like external facing things versus like structs are used for internal stuff, but besides the point. So the next thing that we would want to do here after mallocing is now we want to set the actual values. So we have our item here, and then we're going to set the first value to, well, our value right here. So we want item pointer to value. So this is the arrow operator, which is the equivalent to doing star item and then value, like, or oops, I gave it the wrong name. This is first, and move this all down a little, and this is going to be equal to value. So this is equivalent to a dereferencing item, accessing first, and then setting it equal to value. So now that we have that, now we want to set the rest of it. And so the rest of it is going to be, well, okay, we can access it the same way. So item and then rest. And so once we access this, let's actually take a look at what this is. So rest is going to be, oops, it's Let's erase that. So res is going to be actually a single pointer. And that makes sense because this is just pointing to somewhere else in memory, each one of these. So we can set this to dereferencing list. And so that gives us the first, or the memory address of the first node. So we go kind of one layer of indirection in. So now that we have that, now what we want to do is, well, we have what kind of like looks like this. So we have our LL node double pointer. We have this thing, which is pointed to by item. But now we want to make sure that we set the double pointer thing to the beginning. And so that's why we actually wind up having the double pointer, because what will wind up happening is we want to now dereference list and set that equal to item. So now we're pointing to the very start of the double the linked list. And so if you remember back in ages ago now, it seems, in C, when we wanted to actually edit an item inside a function and then return something that is like still edited and not just like has disappeared, because remember C is passed by value, then we wanted to pass a reference to that. So we wanted to edit the list, which is going to be a series of nodes that point to something else. So to get a reference to something that's already implicitly a pointer, we're going to do ampersand that, and that gives us a double pointer. And so that's why we pass in a linked list double pointer. Does that make sense? Yes. Sorry. Yeah, also if you need to head out, feel free. It's gonna probably end in like a minute. Okay, cool. Yeah, of course. Yeah, if there are any kind of lingering questions, I'll be around packing for like another 2 minutes. So yeah, thanks for coming, and feedback link, same as usual. So yeah, good luck this week.